the first page of the final exam, just like any other exam, is going to be the ranking questions. The ranking is going to be asked based on the activity, stability, all the things that we talked about. Definitely, acidity is our favorite questions. So, especially we talked about the different types of acidic hydrogen on carbons in the very last chapters. So this is something that relevant to that. So the question is asked to rank these molecules based on the acidity, and your first job is finding out what would be the most acidic hydrogen on each molecule, right? I mean, there is an alpha hydrogen next to carbonyl, but that is not the most acidic hydrogen there, right? Because this is a carboxylic acid. The most acidic hydrogen is definitely the hydrogen on the carboxylate. So you got to find out the most acidic hydrogen. Don't just mechanically finding out the alpha hydrogen as the others are showing them. But this molecule, the most acidic one, is not the alpha hydrogen, it's this carboxylic acid. So don't get fooled by that. But this one, clearly the most acidic hydrogen is the one that in the alpha positions, right? And then the other one, that's the one that we talked about, the true carbonyl will stabilize this carbon extensively by the resonance structure, so it should be the most acidic. And aster also have an alpha hydrogen, somewhat acidic. And even though there's no carbonyl here, the most acidic hydrogen is the hydroxyl hydrogen, because that's a pKa value is about 16. So keeping up the pKa numbers, acid, that's about 4. It could be between 4, 3, and 5 regions. Acid is 4. This acidic, the alcohol, just regular alcohol is about 16, right? That's what it is. Now, we're going to talk about what would be the conjugate base looks like when we take the protons off. So if this proton goes away by the base, you make this enolate that is stabilized by the resonance structures. That's why the proton at the alpha position becomes acidic. And that pKa values of the one ketone is about 20. I mean, the reason I keep saying these numbers, this is kind of a reference number you can use to sort things out. So the alpha hydrogen of the ketone, the pKa value is about 20. And this is a one that when you take these protons away, you get the carbon ion surrounded by the two carbonyl. So you can see that it can make the resonance structure with this carbonyl, but it can make the resonance structure to the other carbonyl. So that certainly stabilizes anion more. We expect a high acidity. The question is how high that will go, right? So you may want to remember that the acetoacetate, right? We talked about the malonate with the CH2 sandwiched by the two aster. That's about the 16. Acetoacetates are ketones and the asters. That's about 13. These ones are two ketones. So I'm expecting this one's even more acidic compared to acetoacetate. It becomes about 11. So that's, asters always, lower acidity compared to ketone. So having those two ketones surrounding those methyl, the proton acidity goes up.
Would there be a difference in acidity on the ketone on the right side and the left side?
Yeah, there will be slightly different. If you take these protons away, you're gonna make a more substituted double bond there, right? And like this one, compared to double bond over here. So this one's about 20, that was about 21. It's about a tenfold difference. Now, this is an aster. We talked about the hydrogen at the alpha position of the asters about the 24. We talked about that in the when we discussed Claisen condensation. So this is kind of typical numbers. So if you knew these numbers, you can basically point out that the most acidic one is clearly this. That's why I don't want you to fool by these carbonyls. You notice that there's an alpha hydrogen there. Everything else alpha hydrogens, but the most acidic hydrogen in that molecule is a carboxylic acid. So second one should be this one. Surprisingly, even though this is a hydrogen bound to the carbon, this hydrogen is more acidic compared to that one. Right? So most of the time, the hydrogen on carbons doesn't become acidic, but when they are substituted by like these two carbonyl, it really increases acidity a lot. So that hydrogen is more acidic than even this one. So that's number 2. This is number 3. And then clearly this is number 4, and that's number 5. Now you know all the spectrum of the acidity of the molecule we discussed in organic chemistry. So you probably want to review that to make sure that you can sort things out properly. The second question here is rate by the hydrolysis, right? Hydrolysis is cleaving the function of anything, cleaving it by the water. But the question is asking the hydrolysis in the basic condition, right? In the case of basic condition hydrolysis, one of the reagent is a hydroxide. Hydroxide is going to make an attack to the carbonyl of this dioester, and then that will make a tetrahedral intermediate. This will make this carbonyl bad by kicking out this thiolate. So that's the mechanism that we've been talking about for the carboxylic acid derivatives, and that's the purification mechanisms. And then what I want you to pay attention is, I mean, obviously the hydroxide will attack all these carbonyl, but what are going to be different each molecule is the living groups. This one, we are kicking out the thiolate. That's the one we kicked out. In the case of the regular ester, what's been kicked out is methoxide, right? And then the next one is going to be the same thiolate, but the benzenes on sulfur. And that clearly does something like the resonance stabilizations. And then that one is the same thing, but we got the methyl substituents at the para position. So we'll talk about the substitution effect. And then this one, what's going to be kicked out is going to be the amide. I mean, here you can easily see that which one's going to be the worst living group, right? The worst living group is going to be the least stable anion, and that has to be this one. So this is clearly not going to happen, so that would be the worst one. Which one is the best? And then we need to talk about the stability of the living groups. This sulfur with an anion, that is a bigger anion compared to the oxygen with an anion. So that is a better living groups. We talked about it since the chapter, I don't know what chapter was it, long time, stability of an anion. And then this thiolate, those are the better living groups than this alkoxide. But there's 3 of them. So which one would be the better? So you're going to use other factors like the resonance structures. For instance, the thiolate with the benzene substitute on it, we can see that that can come in and make the resonance structures. Now the benzenes are taking the electron density in, and it'll look like unstable because the benzene aromatic is broken, but it's just temporarily. I mean, you know that there's none of the resonance structures actually revealed. This means that electron density of the benzene goes up. It goes up at the ortho positions. It also goes at the para position. It also goes at another ortho positions, and also sulfur also taking a higher electron density. All these electron densities are distributed to 4 points: sulfur and 2 ortho position, para positions. That is actually what is going to be. The resonance structures are only pointing out the extreme possibility. They're never going to lose aromaticity like we show in the resonance structures. It's just merely increasing electron density or those positions we talked about. So benzene will never actually lose resonance structures in realities. However, benzene takes care of the sum of the high electron density, so that will stabilize this thiolate more than that thiolate that cannot make any resonance structures. So this is definitely better living groups compared to that one. Now we need to talk about between these two. I mean, having the methyl groups there, I mean, that is not going to stop the resonance structures. Only thing it does, it's going to be methylated by depositions. So that's going to be negatively charged. Having the methyl groups there, having no methyl groups there, will they make the differences? That's the question. Right? Well, the alkyl groups is something that we will consider like the no living groups. This para position is going to be negatively charged. And then you have a methyl groups there, that's going to increase electron density even more. So there will be less stable anion compared to the one that without it. So having methyl groups there is definitely lower the stability of the carbon ion. If it's a carbocation, the methyl substituents will make it better, but we are talking about the anion. And then you don't want to increase the negative charges more by having methyl substituents there. So between these two, I mean, the difference between these two are pretty small. This is an inductive effect, small fine-tuning of the stability, but it will make it worse. So which one's going to be the better between these two? This is going to be the better. If you got the electron withdrawing substituents there, that will definitely help because we want to lower the electron density by some way. So electron withdrawing groups will help, but electron donating groups will make it worse, right? So which one's going to be the best one? I will pick this one because of the resonance structure that we make it. We know electron withdrawing groups are on the way. And the second best one is this one. I mean, we'll go down to the worst one. Second best one, this one. And then thiolate is still better than the oxide. And then, so that's how the ranking goes. So it's always the same question. Acidity and these type of things always talk about the stability of the intermediates, of the cations, and but you got to think of in the concept of how you stabilize it. It is electron-rich species, then electron withdrawing groups will help. If it's electron deficient species, electron donating groups will be helping. So it depends on what you will end up discussing based on the questions. All right, this third question is ranking by the basicity. You know, basicity is a kind of a how we can easily take out the proton. That's how the base works when you're looking. So in this molecule, which part is the basic part? It's a nitrogen, right? The carbon doesn't have a lone pair, so there's no way the carbon becomes the base unless it's negatively charged. But nitrogen is going to have a lone pair. So this question is asking, where are the lone pairs of the nitrogen in the molecule and how they are situated? So this particular one here, that's a CN125, right? Nitrogen lone pair is on sp orbital. And then sp orbital, something that you also need to think about in the acidity or the stability is the orbital actually matters. The more S character it has, the electron is going to stay more close to the nucleus, and then since the nucleus will be positively charged, the electron becomes more happy. So when S character goes up, these lone pairs are not going out trying to take the proton because they are happy bound to the nucleus. So this is not really basic lone pair there. And then, and this is basically what I was talking about. And the next one, there's a lone pair there on the pyrrole. But this lone pair is, this is used for making the resonance structures. This is an aromatic molecule. These are 2 electrons from this double bond, 2 electrons from the other double bonds. That's not going to be enough to make an aromatic molecule. Remember the Fickle rule? The Fickle rule is determining the aromaticity of the molecule. There's a 3 checkbox we need to do. 1, it should be the annulant. What that means is all the atoms in the cyclic structures should be sp2 hybridized, right? And then it's got to be planar structures, right? Second positive, got to be planar structures. And the third one, number of the pi electron should be described as a 4n+2 formula. Right? So 4 electrons from the 2 double bonds not going to be enough. So we need that 2 electron of the nitrogen lone pairs to make the 6 electron as a pi system, and that's what makes it aromaticity. So these lone pairs are definitely not there for picking up protons. So this is going to be very, very not basic lone pairs. And this is cross it out. I made it wrong. If you you may be able to proton if you really push with a strong acid. Then if you ever protonate this nitrogen, that is not going to be a aromatic. So this is wrong. I don't know what I was thinking when I write it down. What would you describe this? It is not an aromatic molecule, right? I'm kind of already revealed that this is not anti-aromatic, so that will be non-aromatic. This nitrogen, when it's protonate there, it's going to be sp3 hybridized. Even though it's a positively charged, it's not sp2 hybridized nitrogen. This is the sp3 hybridized nitrogen. So if you got any of the nanomolecular structure lose sp3 hybridizations, it becomes sp3, you just got that annular structure broken. There's no full conjugations. So it won't be aromatic structures. It even won't be anti-aromatic. So this is definitely because of non-aromatic protein. That is something that I may be wrong, so cross it out. Anyway, the pyridine, we know that these lone pairs of nitrogens are sp2 hybridizations. sp2 is better than sp orbital of this nitro. This will be somewhat basic. I mean, that's the reason why we use a pyridine as a base if you ever need to take the protons away. This nitrogen has a lone pair there, that's an aniline. That's the question that we've been asking a lot since the locate one. Hybridization of the nitrogen aniline. Even though these nitrogens are 3 bonds there, but this is not sp3 nitrogens, right? We talked about how the nitrogen next to double bonds, you need to, this nitrogen lone pair is going to make a resonance structures. So in order to make a resonance structure, so that has to be stay sp2 hybridization, even if it looks like sp3. So because of that, this nitrogen lone pair is going to sp2. And that is the one truly becomes sp3 hybridized one, the most basic one. This is basically the most basic nitrogen there. And then the second basic nitrogens, in my opinion, is going to be the pyridine, because that just stays in sp2, never make any resonance structures. This is the one that, not only doing that, it makes a resonance structures, electrodensities is definitely withdrawn by the benzene ring. So that's why this becomes number 3. And then this is a kind of a dilemma there. I mean, this SP would make it much less basic, but which one's going to be worse between these two? Is this a lone pair that separate aromaticity or the ones in the lone pair? So you may think that, I mean, that makes aromaticity, so definitely not available at all. You may think this was number 5 and that would be number 4. But between the difference between these two is so small. If at that time, if you ever write this way, we gave the full credit. The reason why we gave a full credit for that answer, making that was a more basic than the other one, is that this molecule, I don't talk about this nitrogen, I talk about this molecule, because we're talking about how basic this molecule is, right? The basicity coming from this molecule is not the nitrogen lone pair taking the proton. The basicity of that molecule is going this way. This lone pair is coming in, and that goes out, and this pops out. You put the hydrogen on the carbon. That's how this molecule would react as a base. Not the nitrogen getting the hydrogen. This is not going to be made. This alpha carbon to the nitrogen, that's the one that gives the hydrogen. So this is how this molecule will act as a base. So it is a somewhat basic by this way. So that's the reason why we take that answer as a correct answer. I'm just going to point out this. I mean, this is kind of a somewhat very special situation, so you can't forget about it if you want to. I just want to mention that. Yeah, this molecule becomes a basic, not because this lone pair picking up the proton make this, it's because of that lone pairs coming in and then goes over, and then these alpha carbons are reaching out, pick up the proton. That's how this molecule activates. The chemistry sometimes is very strange. All right, the second question is something that you never seen before, but at least you know the concept. I mean, this molecule here is a sulfur with a positive charge, and then we'll describe that something like a Briggs reaction, which is a phosphorus eolide. You can make an eolide with a sulfur, and it's a sulfur eolide. And then the sulfonium ion, which is sulfur positive charge, if you're using a strong base that we use, you can take out the proton from this carbon and make an yielded. And yielded is definition of the yielded is that you have a positive charges and negative charges in adjacent positions. So that's the yielded. So phosphorus can make a yielded, sulfur can make a yielded. If you want to talk about further, silicon can make a yielded because a lot of different things can make a yielded. But anyway, so this is what it is. And then they will react with the carbonyl. And then the Wittig reactions, the phosphorus yielded with the carbonyl to keep an aldehyde, make a double bonds. But sulfur yielded does different thing. It makes an epoxide. And then the question is asking, explain how the reaction will occur. So what would be the first thing to happen? Right? The same thing as the Wittig reactions. This is a carbon ion, carbon with a hydrogen density. That's a nucleophilic carbon. And then we got the electrophilic carbonyls right there. So just like a Wittig reaction, the first step is that this nucleophile making a tetra electrophile. Right? That is basically everything that many reactions we talked about in the carbonyl. Ketone and aldehyde reaction go the same way, carboxylic acid replicate the same way. Even though all the reactions and all the reactions we talked about chapter 22, some are different, still the same thing. The nucleophile makes a type of electrophile. This is a nucleophilic carbon because of the anion there. And then the carbonyl carbon is electron deficient. The first thing we can expect is that this high electron rich species going to make an electron deficient carbon of the carbonyl. So that way, this becomes an alkoxide, and then these dot things attached there. It almost looks like a green. That part is something that I wish you can recognize it. The second part is going to be the difficult if we don't give this clue. But we give the clue that what's going to be formed is an epoxide. So you have to figure out how to make an epoxide from there. And I wish that you notice that this sulfur with the two methyl groups, I mean, it's possibly charged because this carbon is attached to that. But that means that this part could become the living groups. Just like we can kick out the neutral amine as a Hoffman elimination reaction, we can kick out the neutral waters out, the hydration reaction for alcohol. We can kick out this dimethyl sulfide as a living group. It's a neutral molecule, so that's a stable living group. But that happened by maybe oxygens making a path there and they kick these living groups out. So this will make an epoxide. These reactions are not discussed at all in during the class, but concepts are pretty much similar. The yielded is a nucleophilic because the carbons are negatively charged, and that is the one that makes an effective carbon in the same way as a Wittig reagent works. The phosphorus yielded making an attack to a carbonyl, but they get processed different way because the phosphorus, when they goes out, they take out the oxygens out, so they get a double bond. But in the case of this sulfonium ion, it can kick out this neutral sulfide out, so that's the reason why you get an epoxide. So it's just figuring out how this would work. That's what this question is asking about. And then the structured product is this one. So I know this question could be difficult, so it's just a matter of how you can follow the concept and try to explain how things out. I know. All right, the next reaction is providing a reagent to make this series of the conversions. So there are 5 reagents set, you need to provide. In order to make this one, from that, you have to carboxylate to the position having the bromine, right? So there's a different way to do it. We discussed each one of these conversions many times in the questions, but now I'm trying to put it, but the space is limited. I may not be able to put everything, but at least I'm trying to show you several different ways. One, you can make a Grignard, right? If you just put the magnesium there, you can make a Grignard. But then you need something like electrophilic carbon to get attacked by the Grignard. Then easily that would be the carbon dioxide. Carbon dioxide, that carbon, you've got 2 oxygen bound to that, makes it electrically deficient. So that's the carbon attacked by the Grignard. You can make the carboxylic acid this way. If you don't want to use a Grignard, that's fine. There's another way. You can easily think of the carboxylic acid becomes the cyanide and nitrile. So you can easily replace the bromine with the sodium cyanide. Then once you get the cyanide there, what you need to do is hydrolysis. You put it in acidic water and then heat it up. And the cyanide nitrile will become the carboxylate. So there's a two different ways, but there will be more in it, I'm pretty sure. If you want, you can use a Grignard. You reacting with a formaldehyde, that will make a primary alcohol. You oxidize the primary alcohol to carboxylic acid. That will also make a carboxylic acid. There's so many different ways. As I said, I just don't have a space for all of them. But these two are just a couple of examples I can show you. But there will be more correct answers. That's the one we're going to look into when we're grading these questions. And the next one, you have a carboxylic acid converting to an aldehyde, right? I mean, there's no way you can convert the carboxylic acid to aldehyde directly. You gotta do it a different way. One way is reducing completely to the primary alcohol by drinking aluminum hydride. Don't try to use sodium borohydride because sodium borohydride doesn't have power. Sodium borohydride can only work with a ketone or aldehyde, right? Or imine. That's it, nothing else. So you need a lithium aluminum hydride. But the primary alcohol, you still have to oxidize the aldehyde. And then we talked about so many reagents. I mean, of course, that would belong to test one, but you gotta know everything because it's the final exams. You can use a PCC, PPC, and chlorines and even sworn oxidation and things like that. This is the one way. Another way is you convert carboxylic acid to an acid chloride, then you need a diamine chloride for the reagents. Then you can use a very weak hydride. That weak hydride is a lithium aluminum hydride, but with a 3-ketetoxide ion. That 3-ketetoxide makes it the power of the hydride weak, and that's the reason this can only react with aluminum hydride and acid chloride, and then so you can only have it out there. So there's a couple of different ways to do that. And the next one is, it looks pretty similar. This one, that one, only difference is having the methyl groups hanging out that position, right? That's the only differences. So you gotta methylate the alpha position. So you gotta search the reaction that you know. If you ever know any reaction that could alter change at the alpha position, then you gotta use an enolate. So if you have a base, then you can make an enolate there. I mean, of course, you can make a base and an enolate with different types of base, but LDA, in my opinion, will be probably the best choice here because it will quantitatively convert all of the starting material to the enolate. And then that enolate is going to stay there until you add it out the halide. So it makes an SN2 reaction there, so you get the methyl group put on, and that will be the ones you make. If you want to do this reaction in the conventional base, like sodium alkoxide, right? The oxide, you won't get this. That reaction is going to be a bit complicated, so I'm not going to show you. If you're interested in, ask me later, I can show you that. But you need a conversion of all of this into enolate. I mean, just briefly talking about it. Why the methoxide, sodium methoxide wouldn't work in this molecule here? If you use a sodium methoxide, you're not converting everything here to there. You only convert small fractions of that. So let's say you got majority of this material hanging this way, you got 1%, I mean even that 1%, it's like 0.1% made this one, and that one will react with that one directly. You know what the reaction is. That's an outdoor condensation. So if you're using a sodium methoxide as a base, you are actually going to make an outdoor condensation. They're not going to wait for the alterations. So that's how things can get complicated. That's why choosing the right base sometimes will be practical and very critical. So anyway, that's the reason I suggested using our data there. Makes that everything convert quickly, and then there's no other starting material left over, so there won't be no outdoor reactions. Only thing that happens without the enolate is basically the alkylation reaction with the methyl bromide we provide.
So that's the how I think it should be created. And the next one, you may think that this is this, it is not. I mean, if you look at that, this is this one. So this aldehyde is getting reacted with the double bond here. And then we got the carbonyl next to it. The conjugated, I mean, it could be hydroxyl groups there, but the conjugated carbonyl is kind of giving it away what reaction happened, right? What we need to put on, by the way, these reactions can also happen by the enamine, right? If you're using the enamine, make this the imine ion first with the secondary amine, and then you will make an enamine there, and then you cover the same thing. You will basically make a substitution reaction there, but enamines, this imine ions are hydrolyzed in the end by the water, so you can make that in a different way. You're either using LDA, make enolate made by the LDA, or you can make an enamine and then go for an oxidation reaction. And now coming back to these reactions, this part is that part. So this is a carbon, used to be the carbonyl. So you may imagine that we need to have some kind of nucleophilic carbon next to carbonyl, making attack to this aldehyde. So if you figure that out, this is an aldo reaction. So you need a new profile. This ketone, the acetone, you need to take these protons away, so it makes a nucleophilic enolates right there, and then that's going to react with this one. So it attack that positions, and then you're going to get the hydroxyl groups there. But the hydroxide and then protons on the alpha position can go away, and then you're going to have a double bonds created. I mean, you can do it either acidic condition, even in the basic condition, you may get the elimination reaction happen. So you will get the alpha beta unsaturated ketone. So this is all those reactions. The question is, yes, where are you going to get this enolate? That enolate, that would be coming from the acetone, right? I mean, acetone, but you need to have some kind of a base. So you can use sodium methoxide, or you can use LDA, either way. As long as you can take the protons away, that's going to make an attacking aldehyde, and it will create that. So that's just aldo reactions. And now somehow the molecule grew further, right? This is way bigger now. This is a kind of a thing that you've got to recognize what things happen. This is a part that is this. So this part is this, and this double bond used to be this one, and this carbonyl is that one. This method would be that one. So if you figure it out, which part of the product is a starting material, right? Then that will be, you need some reagents not highlighted there. That's what we need. But what is the first reaction to happen? Remember, this is a conjugated ketone. What conjugated ketone does, because nucleophile enolate, it does microaddition, 1,4 addition. So we need some kind of nucleophile attacking the beta position of the carbonyl. I mean, the alpha-substrate ketones. So this portion 6 member ring, I would say this is a kind of carbonyl here. You get the enolate created by adding a base. The enolate reacting with the conjugate ketone. Because it's a soft nucleophile, that is going to attack the beta positions, and then that push this up and that goes up. You get these intermediates there. But this is not the end of the reaction. This is a Robinson annihilation reaction. Okay. What happened was this proton here is a transport. Basically, you change the enolate at this position to the other side. So this proton switch the position over there. So you make the one enolate convert to the other enolate, and that enolate will see the carbonyl here. So that's where the aldo reaction happens. So this makes a carbonyl of this carbonyl. I mean the carbonyl here, and then these alpha carbons are making effect to this one. You get the hydroxide is here, but dehydration can happen very easily. So it will make this final product. So Robinson annihilation is the molecular addition followed by the alkyl reaction. That's the what it is. The molecular addition, you need to know for that. So that's how you need to recognize this one based on the what is coming from the starting molecule and then what is the one you need to provide. So that's the enolate we use to make a molecular additions. And then once that happens, then this enolate has to change the other one because the ring size is not going to be right. So this will finally make the ring closures, and then these double bonds are basically what is created by the dehydration of novel products. The molecular additions are some of the technical case pretty complicated, but I really wish that you know inside out, front side, back side, everything, because it's ultimately testing how much you understand these type of reactions. Anyway, so this is how things can happen. This question. The next one is asking, this is the sum of the molecule. It's kind of an aster, right? Phosphate aster, not the phosphate aster. This is a type of, this almost looks like an anhydride, right? It's that pyrophosphate. This is not phosphate. It's carboxylic acid. It's connected to the phosphate there. This is almost like an anhydride. This is a very reactive form. I mean, ATP has three of the phosphate is condensed that way. That's why the ATP can be used to make so many reactions. And you're going to find that at the bottom. But anyway, this is it's almost like an anhydride. Now the style of the CoA is a coenzyme A, has a diol there. You don't need to know the full structures, but the sulfur is a nucleophile that could basically make an attach to the anhydride, and then kick this phosphate out, so it becomes into lipid groups, and then you can make that. And then that is reacting to something like choline, that's a bottom molecule, and then it will make these structures. The question is asking, what is the structure of the choline? I mean, you can use that from the product. You just notice that the alcohol is making a packet and kick the CoA in the diol out. So this part must be the choline. Right? So that is clearly what you can imagine. What is a choline is this one. That hydroxyl group is going to make an attack there, and then we're going to have a tetrahedral intermediate. But this come back and kick this lipid group, which is a coenzyme A. That's what you take out. So you're going to see a lot of these type of reaction in biochemistry. That's why this particular material we talked about as a test 2 is directly relevant for the class you're going to take in the next year. Anyway, so this is a choline. You can guess that by this thing attached there. So that's true to the CoA. The second question is, what is the reactivity of the acid CoA if you're reacting on the the regular aster, right? The regular aster means that you got have oxygen there, not the sulfur. So what would be the differences between these reactions and that reaction? You may end up having the same product, but differences are leading groups, right? This question is basically asking which ones are the better leading groups. We already talked about it in the first question. The sulfur is a better leading group, right? It's going to be alcohol there. So the reaction is probably going to happen faster because the diol is a better leading group than alcohol there. And then the acetyl CoA reacting with the 1-butylamine. Well, 1-butylamine is a 4-carbon chain ending with nitrogen there. That's the butylamine. And that's the nucleophile position, right? That's the one that makes an attack. So you get the tetrahedral intermediates. This will come back making a carbonyl by kicking the diolates out. So that's basically how you make the anion. So this is, in a way, the biochemistry that you're going to take later is not a organic chemistry, it's field scale. That's what you can see. So this is just kind of a same concept, just using as a different example. You're asking whether you understand the concept. Then you're going to face a lot of reactions. Well, the reagents should give you an idea that what you need to remember, especially the Hoffman elimination reactions. You're gonna have an amine, but you're reacting with the excess of methyl iodide, methyl bromide, probably providing the base. Base is not shown here, but that is kind of assumed. And the second step is a kind of a silver oxide. Silver oxide role is exchanging the halide, the iodide, the conjugate counter anion to the hydroxide. So that's the new profile there. So basically, the methyl iodide, once it's going to make a 1 or 2 groups, it's going to react again twice, and then 3 times in order to make a quaternary ammonium is there, right? That counter anion is going to be iodide, and then that iodide will be replaced by the hydroxide by the silver oxide. So that's why we do the second step. By heating it up, you're going to make the E2 elimination reactions, but this is a very, very bulky living groups. I mean, this is a ammonium groups there, but once it goes out, it's going to make a neutral closure amine. That's why people think about living groups. It's going to pick up the hydrogen from the less substituted side because the bulky living groups, makes it the more substituted groups are difficult to make the double bonds. So that's why you get the Hoffman products. But these methyl groups are definitely more less substituted compared to any of these carbon chain there. So you get the double bonds on the methyl side, not really the way. So Hoffman elimination reactions makes Hoffman products. So that's what it is. And the second step, well, now you see that it's a sodium nitrite and then HCl. Those two combination is basically making a nitrous acid, right? HNO2. And nitrous acid makes a nitrosodium ion, which is an N plus. That we're going to mean, first step is basically making diazoram ion. Diazoram ion is a good living group because we can kick up an N2. So you can exchange the variety of the nucleophiles. It can be replaced by the water, it can be replaced by the cyanide or any other things. But if you're using this HBF4, that replaces the N2 with a fluorine. So you can make a fluorination under a very things. So this is the nucleophile substitution reaction. So that is kind of a little easier to figure out how to do it. These questions are probably more difficult to answer compared to the other two. Well, you have a molecule with a 2 carbonyl here, and then you got the sodium methoxide. Sodium methoxide is a base, so it'll probably take out the proton somewhere, and then you got to think about what is the proton that it will take out. It can take out the proton from this, and then it can take out the proton from that position. It can also take out the proton from this position. Right? There's potentially 3 hydrogens next to the upper carbonyl, but which ones are probably most likely taken off is not the one, this one, because this is next to the ester. We know that this is a much less acidic compared to the other two. But still, there's a chance that either these 3 can go make an interlane and then make the product. So if you don't know what to go for, my suggestion is to pursue all the possibilities and then figuring out which ones makes sense more. So let's talk about, this is probably the most acidic proton in this molecule. We talked about, this is next to the ester, so this is about pKa values of these protons about 24. This is next to the ketone, but the more substituted side will make a more stable annual, so that will be a little bit more acidic compared to the other side. So I think these are probably the most acidic protons. So if you take this proton off by the base, then you're going to make this enolate. That is what is being created. Enolate is a new profile. And then you have a carbonyl there. So we may imagine that this makes a attack there. And then it's going to make a carboxide as intermediate. Why as an intermediate? Because it has a living groups. We can get the carbonyl back by kicking this methoxy out, and you get very strange molecule. Many of you probably shaking your head because you see the three-member ring. Yeah, probably that's the reason I would think that this is not going to happen. Ring constrained molecule doesn't easily produce this way. But anyway, so that's what we can imagine. Now, if you think about taking that proton, second acidic proton in the molecule, then you're going to have an inner ring right there. And then clearly that is the carbonyl of the aster on the other side of the molecule. We can make an attack, but this way it will make a 1, 2, 3, 4, 5 member ring. The 5-member rings are very common in nature because it doesn't have a rings constraint. So it's very reasonable. And then this will make a tetrahedral intermediate, but we know that it will come back making ketones and kicking out these toxic groups out. So we may get this ketone as a product. As a third possibility is taking out this proton next to an aster. If you take these protons away, you've got anions here, you've got the carbonyls and ketones. If that react, we're going to have the same three-member ring. And then this was a ketone. We don't kick anything out. There's no way you can, toxic groups comes out and kicking the methyl groups out, right? That's the difference between the Aldo reaction and then Kleisen reaction, right? I hope you remember that. The difference in ketones and aldehydes comes to the acid derivatives. Among these three, I don't think this will happen because three-member rings are so constrained, it cannot be happen this way. But that is definitely reasonable. So this is a probability more difficult to figure out than if you just do everything and then the outcome is basically you will figure out which was the most likely happening. So some of you are wondering, because this is the most acidic proton, maybe these ones are produced the most. Right? Why? I mean, but this one, even though it produced, this doesn't reach the product. So what happened, I can guess, is it get the deprotonation happen. You get this one. You get this one produced, but instead of going here, because you cannot get there, if you go there, you get the three-member ring produced. It just hangs around, and then this one just pick up the proton back, and then it will come back here. And then nothing ever happened by doing this way. But once in a while, this proton goes away, and it will reach the formula product. So the chemistry is a very dynamic situation. You will try things, but it doesn't lead to the products, and sometimes you can come back and restart. So that is possible because all these reactions are reversible until it forms a product. All right, the next reactions are somewhat easily recognizable because you got the trifene and phosphine. You don't have many trifene and phosphine in organic chemistry unless the big reaction, right? You don't see the trifene and phosphine anywhere else. So that is going to be the base. That should be the clue. That is the base in making a phosphorus ion. And then the phosphorus ion reacting with the aldehyde, it will basically make this in an intermediate. We know that this is a nucleophilic carbon attacks an aldehyde, just like a 3 yards make an attack to an aldehyde, ketones and aldehyde. Right? Same way, that makes an attack. You got the alkoxy groups there. But oxygen anion really love the phosphorus, especially the phosphorus here is positive charge. So they're just going to click in. You're going to make a phosphatane, make a 4-member ring created. But that molecule is not stable. Then you're going to be this clip. But not clipping the bond they created, they rather clipping this bond and that one. So this one goes out as a trifene phosphate oxide, and then that one goes out as double bonds. So that is how the Billig reaction works, right? But if you think about it, the initial reactions are basically the nucleophilic carbon of the Billig reagent attacking the carbonyl the same way 3 yards makes an attack to carbonyl. So you can talk about the same reaction over and over again. Even the new reactions do the same concept. I just want you to see that so it will make crystallinity. One other thing is I want to mention that the Vedic reagents can react with a ketone or aldehyde. That will make the double bonds. They don't react with an ester. They don't react with an amide. None of the carbonyl of the carboxylic acid derivative work with the Vedic reagents. Only ketones and aldehyde. Don't try to use a Vedic reagent for any carbonyl. That's not happening. Only ketones and aldehyde will work. Not the carbonyl of the carboxylic acid, not the carbonyl of the ester, not the carbonyl of the amide will react with the Vedic reagent. All right, the second reactions here, we got ketone. The butane is a strong base and then low temperatures. So we have a ketone here, but you notice that there's a ethyl groups here, methyl groups there. We got two differently substituted carbonyl. So this is almost looks like this is a question about the thermodynamic enolate and kinetic enolate. So just want to remind you, what makes a kinetic enolate? You need to have a bulky, strong base at low temperatures. That's what you need to make a kinetic enolate. Anything else will be thermodynamic enolate, but typically weak base and high temperature. This is the butyl are not really huge base, but you notice that it's a low temperature, it's a strong base. So this is probably satisfying the condition to make a kinetic enolate. So with that, I would imagine this process goes out, you get the kinetic enolate, which is a last substitute alkyl chain, we use a proton. Then they will react with the alkyl halide by SN2 reactions. By that, carbon makes an attack there, kicks it out, catches SN2 reactions. So you get this. So you need to figure out what particular created based on conditions. If you're using a weak base, for instance, like a methoxide, then, I mean, even LDA at the room temperatures, that will basically make the thermodynamic. That position will make the cell effect. You get the methyl groups in the wrong positions. If you choose to work with a wrong enolate, you will get the wrong products, so you will get a functional credits. But you know, that's the reason why you got to pay attention to conditions. All right, the next question is it's kind of a series of the steps provided. This is diol, right? Ethylene glycol. And we got aldehyde and ketone, but we only adding one equivalent of the ethylene glycol. So that will make acetal. So only one carbonyl. Then which one will it be? It will be aldehyde is going to make acetal, or ketone is going to make acetal. That's the question that we face first. And then for that, I want you to remember the reactivity of the carbonyl species. The alkyl chain will lower the electron efficiency of the carbonyl, make it less reactive for the ketone. Not only the electronic reason, the carbon chain increases steric hindrance, so that's going to make it more reactive for the ketone. So aldehyde is more reactive than ketone always. So if you have a nucleophile coming in, which one's going to be hit first? Aldehyde. Aldehyde is the one that reacting with the diol, so you get the acetal forms first. Then this carbonyl of the ketone, now that can be attacked by this nucleophile, which is a cyanide. Cyanide makes an attack, and this reaction is called the cyanohydrin reactions. Anyway, it's just nothing but the cyanide acting as a nucleophile, attacking the carbonyl, and then this protonation of this alkoxide to alcohol. And then the third step is you are cooking in acidic water. That will break this acetal to the aldehyde, right? That's how you break the acetal. But not only that, we have a cyanide, nitrile, that can be further hydrolyzed to the carboxylic acid. So nitrile will become a carboxylic acid. Not only that, this acetal also to be same aqueous acidic water to the carbonyl. So you get an aldehyde back. So you should be able to follow the step. Sometimes when we give a, you need to figure out which one's going to react, because it could be the possibility of the reactions. All right, so hopefully this is somewhat reasonable. The next one, hydrogen peroxide with an amine. This is something you need to know. Hydrogen peroxide is an oxidant, and then that will oxidize the nitrogens. But especially the tertiary amine, when you got the peroxide, it'll make the an oxide. Nitrogen becomes an oxide. That is a basic carboxyl group there. And then that can be the one pick up the proton, make the double bonds. So one of these reaction, this is a co-eliminations. I mean, sometimes you gotta know your reagents. Some of the organic chemistry requires a memorization. So this is one of the case. Then recognizing, yeah, this is a co-elimination reaction. So you're gonna oxidize this nitrogen to an oxide, and that will pick up the hydrogen from the less substitute side, just like Hoffman products would make the Hoffman elimination reactions. Then you're gonna make a double bonds by kicking out this hydroxylamine goes out. So you get a double bonds on the less substitute side. So that's a co-elimination reaction. This question, I believe we just gave it as like a gimmick. This is very simple. Sometimes when we provide too simple question, then your mind go crazy. That cannot be that simple. This one, yes, it is. It is a simple question to ask. But, so, I mean, this is a secondary amine reacting the ketone. We've been talking about this many times. This going to make an attack, you get the carbon on amine, but this will be protonated so you can kick the water molecules out by making an iminium ion. But you don't think, you shouldn't put that as an answer, because that is not the correct answer, right? Iminium ion with the alpha hydrogens available, it will be taken out by the base, you're going to make an enamine. So that is an answer. I mean, if you think about how this enamine is going to get used, no, then we don't see anything else. This is what we're going to provide, what we're going to make it by this way. So sometimes, yeah, at that time, here's this cannot be it because that number used for something else that was missing. So they were overthinking something they could do something else. This question was actually asking whether you figure out the producing enamine or imine, you were trying to figure out with this question. I mean, obviously, if you answer that, you get some decent partial credit. But the correct answer is because alpha hydrogen is available, so it'll go away with the nitrogen neutral. So enamine is the end product. The next question is something that we talked about. Ketone reacting the bromine and the base, right? This is kind of very strange conditions, but this is the alpha bromine, alpha halogenation reaction base conditions. If you let it happen a lot, you can basically make it, this thing goes out, make an inorate, and that, with the bromine, you got the one bromine edit, but this can happen again. Eventually keep the methyl group size of tri-bromo methyl groups. So you get that things leave out, and then you get the carboxylic acid. This reaction, first step is a haloform reactions. Since it's a bromine, we should call it bromoform reactions. So that is making the ketone as a carboxylic acid. So this is a part that I told you is kind of very strange unless you know this reaction. It's a haloform reaction. And then once you got the carboxylic acid, the second step is carboxylic acid, alcohol with the acid catalyst is a basic recipe for making acid. That's a Fischer acidification. So that part that you can figure out. The first part is definitely something that you need to know to answer. So it's kind of a very unusual information, but that's what I'm
Make sure that it won't
the other side? Well, first, either side will go first. And then the one that has been bromine is going to go acidic. So it's going to happen in the same side. Then once it happens, then it will kick and goes out. Once it becomes a carboxylic acid, these alpha protons is much less acidic. So it's not going to happen to the other side. All right. This question was how we can look through this strange because we give the one molecule, nothing else. We just heat it up. That's all we did. But what we need to remember that is there is a nitrogen that could be nucleophilic, and then aster is electrophilic. So this nitrogen makes an attack there. You get the tetrahedral intermediates, and then when this comes out, make the carbonyl back. You can either kick this amine out, you can either kick this carboxyl out. And which ones are better living groups? Definitely the hydroxyl groups are better living groups. So if it kicks out this way, then you are switching these two. It's kind of connected together. This is kind of a amide formation, making out an amide from aster that happen to be intramolecular reactions. So it's kind of something that if you know the mechanism, you'll be able to figure it out. But if you memorize there is then this reaction might be difficult to find out. So this is just nothing but nitrogen as a nucleophile, makes an attack and kick the alcohols out. But since it's an intramolecular reaction, alcohols are not lost, still bound in the products. So this is how it goes. The next question is somewhat analogous to the previous question I asked you before, right? We got the anhydride here, right? But different asymmetric anhydride. These are CF3, 3 fluorines make it more electrically joined compared to the methyl groups. So this carbonyl is a more electron deficient to get a carbonyl. So when the new profiles comes in, which carbonyl is going to get attacked first, it's a probably more electron deficient carbonyl. That will be the ones on this side, the 3 trifluoromethyl side. So with this new profile, it's probably going to attack that one first because it's more electron deficient. And then that will make a tetrahedral intermediate. It's going to come back and make a carbonyl, but that will keep this acetate out as a living group. I mean, acetate is a pretty good living group if you go. So this is an asymmetric anhydride going through the reactions. Then I want you to figure out which one's going to go. So it's kind of relevant to the questions that I asked you. And these ones are, it's pretty reasonable. I mean, you can easily figure out. This one, you cannot make an enolate, right? You know that. In order to make an enolate, alpha carbon should have a hydrogen there, but there's 3 methyl groups there. So this one, you cannot make it a nucleophile. You cannot make an enolate from it. Only enolate you can create by mixing these two together is cyclohexanol using proton there. So you make a cyclohexanol enolate. That's the one that makes an attack to the aldehyde. This is just a regular alkyl reactions, but we are asking which is a nucleophilic side, which is electrophilic side. That's what it is. If you decide to take this hydroxyl groups away with the double bonds there, I mean, we will take it as a right answer, but this is the initial product of the alkyl reactions, but this is a product output. All right. The next one is how are you going to make it from that, right? I mean, in order to do that, you have to take these isopropyl groups away, right? Because it will be you got to make an amide. In order to make this amide, you need a carboxylic acid like this. If you have a carboxylic acid like this, then you can make an amide. Then how are you going to take this one away? That's the question. I mean, some of you may think that, oh, well, since we know the ketone can lose an alkyl chain by the haloform reactions, unlike the one we showed before, why are we just hitting up with sodium hydroxide bromine and then we can alternate this, dominate this position, and we can keep it out. That is not going to work here. Why the holophone reaction in the previous example works? Because that's a methyl groups. It's gotta be methyl groups. You need to have 3 halogen on the methyl groups so they can lead. 1 halogen, they're not gonna make it lead the proton chain. 2 halogens, not enough. It's gotta be 3. That's why the methyl group has to be. None of this side is gonna be methyl groups, so this thing's not gonna work. So you cannot just break it away and make it up to the gas about the holophone reaction. So what you need to do, making the carboxylic acid somewhere else. Then you gotta search the reaction that you know how to make a carboxylic acid. And I hope that you remember that if you ever have a double bond, then you could break it up by the oxidative cleavages, then you can make a carboxylic acid. Then the question is, how are you gonna get the double bond from the ketone? I mean, there's no way you can do it directly. So you can imagine that you probably have to reduce to the alcohol. That can be done by either liquid hydride or sodium monohydride. Once you get the hydroxyl groups there, then you can do dehydration. Or you can try to kick out by the ketoxide, take the protons away, comes double bonds, kick out the hydroxide. Would that work? This is the OChem 1 stuff. Hope that you remember that you cannot kick out the hydroxide that easy. So that is not working. There's no way you can kick out the hydroxide from the alcohol. You would rather do it in acidic condition. Dehydration is acidic condition. You protonate that becomes a water molecule. So you take these protons away and the double bonds form, the water goes out. Water goes up at the carbocation and the double bond create as a E1 related. That's how the dehydration works. Not this way. So I really wish that you still remember 0.1. Some of the stuff still need those things. Anyway, that is created, and then you can break it up by the oxidative cleavages. Permanganate would be the one to choose because that will make this part as a carboxylic acid. Simply substitute the side becomes a carboxylic acid. Then once you have that, then you can activate the carboxylic acid to the acid chloride, like the diamine chloride. Then you just have the amine, dimethylamine, to make a amine. So you're gonna analyze a little bit, which part of the starting materials you're gonna carry forward to make the products. What reaction do you know to make it work? Sometimes you have to go separate steps to make things happen. This is the kind of a thing that you need to do. Well, this question here, it's a one-sided, the monocyclic ring becomes a bicyclic ring. I'm pretty sure that you know what reaction you do. That's a Robinson relation, right? For the Robinson relation, you gotta recognize which part is coming from where. So this could be that, but that would be very difficult to put anything the other side. That would be really, really difficult. So it's gotta be that side. Then what you need is this part. That's the part. This is probably the alpha position there. You need to make an innovate. And then this is the one that making attack with something called the alpha beta unsaturated ketone. So that part coming from these double bonds, used to be double bonds, to make a micro addition. But we need to have a carbonyl there to make a micro addition like this. So what happened is that this makes an attack, that's a micro addition, you got that. This enolate should switch to the other side to make a 6-member ring. So when the total transfer happens, then you got that enolate, that makes an attack there, then there's an alpha reaction to create this ring fused with that one. So we make this ring, that ring, hydroxyl groups there. We still have to add these methyl groups, and that has to be used to carbonyl. Carbonyl reduced by the hydroxyl, that is not the concern. You know that reaction can be done by the sodium hydride, the sodium hydride. But how can you put the methyl groups there? This is not typo. You're not missing OH. There's a methyl group there. So how to put the methyl groups there is probably not easily seen by this molecule, but we know these hydroxyl groups can go away as double bonds when you do dehydration. Then you know these things are alpha beta unsaturated ketones again. That you could do the one coaddition, microaddition again. That's a beta position. That's where the methyl group goes. So for the methyl group setting, you need a methyl group as nucleophile, but don't choose a methyl grignard because the methyl grignards are don't do the one coaddition. They are too hard nucleophiles to make a microadditions. You need a more soft nucleophile that will be the dimethyl cuprate. Especially the dimethyl cuprate you got there. This methyl group is going to attack this beta position. And then that's how this methyl group set should be used. Then we add that one here. Only thing need to be done is carbonyls are reduced in alcohol. That can be done by just soluble hydride and you get the final products. So sometimes you got this very complicated reaction, but you got to still the formula to get there. So maybe simple, but maybe you need something more. All right, the next question is NMR. I really wish that you didn't forget about the NMRs and IRs and all these things last, because finding them, you're going to see a question like this. I really wish that you still remember the calculate the degree of saturation, right? And that will help you to figure things out. This is 6 carbon, 12 hydrogen, 2 oxygens. If you degree of saturation, it will be just 1. So we got 1 degree of saturation, and then we got IR 17, 18, and 17. Oh, that's the B. Okay. And, we don't know yet, but anyway, the molecule B has a 2 carbonyl. That's what it basically says. This is a probably ketone or aldehyde. The other one, higher frequency means it an acid. So first step is you need to figure out what the structure of the A, right? That structure A is you need to figure out by the NMR. You got the quartet triplet combination. That's ethyl groups, but this quartet with the 2 hydrogens shifted downfield like this. That means that it should have an oxygen. Right? That's the only way you got this CH2. It should be this much. And then we can imagine that because the carbonyl has to be somewhere, especially aster presence. So this might be the aster. And then we got 1 degree of saturation. So that must be the 1 degree of saturation we define. The other is just an active chain. So what's an active chain on the other side? Well, 6 carbon has to be there. We found 1, 2, 3. So 3 carbons missing. So we got CH2, right? 2 carbons to CH3, and then something with a multiple pick. So that must be, this is probably CH2 next to the carbonyl. That's what's the issue with the 2.2 regions. But this is its last carbon methyl groups here. But the one in between is going to be multiple picks. So that's a propyl chain right here. So that is how you need to figure out what's the structure of the A. That reacting with the base is basically the Claisen condensation, right? You are making enolate with this aster. That aster enolate will react with another molecule of an aldehyde. So that attacks this carbonyl of an ester. Keep this in the FX sound. If you have a beta ketoester form as a Claisen reaction products. So that's why the B has a 2 frequency, ketone and ester, right? 2 different the ion frequency of carbonyl. And then this one is reacting with the base. So you take these protons away, you make an enolase there, that you got the nucleophile and the electrophile, so that 0 groups added there. But the third step, hydrolysis happens, you break down this actual carboxylic acid, but heat it up. So carboxylic acid broken down, but because of this, the carboxylic acid beta pushes to the carbonyl, that's where the decarboxylation happens. So this is something that you should not forget, you shouldn't forget. Decarboxylation happens, this gets the proton to This double bonds come, goes out as carbon dioxide. This makes an enol, but enol becomes a ketone, so that is a structure of the D. So this is a kind of NMR used for test 3, but in your case, you're not getting a test 3, you're getting a final exam. So some of the structural determination questions that you have seen in the test 1 may come again, because now we're asking proving a structure based on spectroscopic information. Math